Good morning, students. Welcome to the class. We are discussing palladium catalyzed coupling reactions. In this class, we will discuss Suzuki coupling reaction. What is Suzuki coupling reaction? Suzuki coupling reaction is between vinyl and aryl boranes. Vinyl and aryl boranes with alkynyl or aryl halides in the presence of a palladium catalyst. Generally, we also use a base here, sodium, potassium, or cesium. That means either carbonates or hydroxides, alkoxides. We use any of sodium carbonates or sodium hydroxide or sodium alkoxides or similarly with these metals. So we use these inorganic bases along with the palladium catalyst. Here not only aryl halides, we can also use a diazonium compound or any other halide. Okay, a diazonium compound can be used for coupling or aryl halide, aryl chloride, aryl bromide or aryl iodide. Any of these reagents can be used for coupling. And the other one is a boron reagent, alkyl boranes. Palladium catalyst, tributyl phosphine, then cesium carbonate, in under these reaction conditions, this halide and boron will couple with each other. So in this reaction also, when you want to predict the stereochemistry of the product, you don't need to worry. What we need to do, just remove this alkyl halide and boron, halide and boron part, and couple both these organic moieties. Now this is the bond here. So we are just removing chlorine and removing this boron functional group, and we are just coupling these two things. So this is the product for Suzuki coupling reaction. You write the product here. So this is a biaryl compound. We can access biaryl compounds through these coupling reactions. Here also we will get biaryl compound. Just remove this part and this part, couple these two aromatic rings. For Suzuki coupling, we need to have boron complexes. Now, how do we access these boron complexes? There were different methods. During reductions, we have seen reduction with the boron compounds, diboron compounds. So there we are preparing organoboranes. So the same reagents can be the same reaction protocols can be utilized here. So either alkynyl boron or alkynyl halide, when it is treated with a diborane reagent, what will happen? Hydrogen will add on one side, boron will add on other side. Hydrogen and then boron. Because these halogens are good leaving groups, so isopropanol treatment isopropyl. So these two bromine halides will be leaving. We are getting this. Then it can be converted. It can be converted to, see here this alkyl group and boron both are opposite, but this can be converted to a Z borane reagent by treating this reagent. So this E will be converted to Z using this reagent. Not only that, we can also treat this with an alkyl lithium or a Grignard reagent. So that will attack on boron. Then halogen is a good leaving group. After alkyl migration, what will happen? Alkyl R dash will migrate here, then boron will come here because halogen is a good leaving group. We again generate a Z alkene, that means initial alkyl group and boron are now cis to each other. Of course, these reagents can be utilized in coupling reactions. Phenylacetylene, when it is treated with thiamyl borohydride, hydrogen adds here, boron adds here, then it is coupled with this alkynyl halide, sodium methoxide is the base, so we must use methanol. Also, what is the product? It is reduced with catechol borane, then it is coupled with this aromatic halide, sodium methoxide, ethanol. What is the product? So you just write the products. So here boron will be adding here, hydrogen here, boron here, then boron will couple with this halogen. So the product is Similarly, here also hydrogen adds here, boron adds here. Boron will couple with bromine. So the product is this fellow. So we are generating E double bonds here. Now we have more number of ways for the generation of organoboranes. We can also generate organoboranes using alkyl lithium chemistry. When aromatic halides are treated with alkyl lithium reagents, here metal halogen exchange takes place. That means butyl anion will take the bromide, so lithiation will occur. Then it is treated with trimethoxyborane. It is treated with trimethoxyborane. Then this anion will undergo nucleophilic substitution on borane. One of the OMe will be leaving. One of the OMe will be leaving. So here the product, from this first it will undergo lithiation, metal halogen exchange. Then this will add to boron. One of the OMe will be leaving. So we can prepare organoboranes from lithium chemistry, alkyl lithium chemistry. Then it is coupled with you write the product. Sorry, O triplet. So here it is O triplet. One more such example. So these are three steps. First add alkyl lithium, then add this boron reagent, then add H plus. We will generate this reaction. So I'll write clearly here. Then H plus, we will generate this. We will purify this, then we will use for palladium coupling. This is a two-step process. So I am giving the preparation of boranes followed by coupling. So here we have prepared the borane reagent. Then it is coupled with this is phase transfer catalyst. What is the product? The alkyl lithium generation of aromatic lithium reagents. This is the second method. Here we will have direct halogen metal exchange so that lithiation takes place. Here this is ortholithiation. This is an example for ortholithiation. The coordinating atoms, either oxygen or nitrogen or any atom with lone pair of electrons, it coordinates with lithium. So the alkyl anion will pick up proton from neighboring carbon. So generally it is called ortholithiation. Then it is treated with boron reagent, and finally H plus that generates organoborane and ortho position, organoborane on ortho position. Then it is coupled with what is the product. And generally most of the functional groups can be tolerated in palladium coupling reactions. So we don't have any side products in the palladium coupling reactions. That is why I said it is atom economic, and we can have variety of functional groups on the substrates. Absolutely, these palladium reagents will not react with these functional groups. So many functional groups can be present. These palladium reactions can be performed in the presence of several functional groups. They don't involve in the reaction. In Suzuki coupling, we use alkynyl or aryl boranes. Not only that, we can also use alkyl boranes. We can also use alkyl boranes. Here is an example. This is an alkyl borane. Alkyl boranes will also involve in coupling. This is the advantage with Suzuki coupling. In other coupling reactions, we must have either alkynyl or aromatic systems. But here, yeah, absolutely, alkyl boranes will also involve in coupling. You write the product. I will mark the coupling groups. So this halogen and this boron part, they will couple with each other. This chemistry is utilized for the intramolecular cyclization here. So 9-BBN will add on to the alkene, 9-BBN will reduce alkene, boron will add to the terminal carbon, then terminal carbon under palladium will undergo Suzuki coupling with this carbon. So when we look at the ring size 1, 2, 3, 4, 5. This is the product here. And next important point about Suzuki coupling is carbonylation. What is carbonylation? During boron reagents, we have also utilized carbon monoxide after boron reagent. So the same chemistry will also utilized here so that we will get ketones. So boron reagent, carbon monoxide, and then coupling group. And then coupling group. So they will undergo potassium phosphate, THF, benzene, So they will undergo carbonylation. So the product is here, boron and halogen will be coupling. So in between we will have carbonyl. In between we will have carbonyl. So NC8H17, it is bonded to carbonyl. Then carbonyl is bonded to alkene. Carbonyl is bonded to alkene. Of course, the stereochemistry of carbon halogen bond will be retained. So it is E. Here also it is E. So this is how we can also do carbonylation in Suzuki coupling reactions.